Hi there, this is Mr. Deiulis, and we are back with AP Physics 1. When I had last left you, we had been talking about average velocity and average acceleration, and I had given you an example problem here, which I still even have worked out, where Bob goes from 0 to 60 miles per hour in 3.5 seconds. What is his average acceleration? And in that case, I had converted the value of 60 miles per hour to meters per second. So that is 26.8 meters per second. I had shown the given values. I had shown the unknown acceleration. And this is what I mean by simply showing it, just all this stuff right here. It's showing that. It's a necessary step. And then in green here, I had shown the equation that I was using. And again, that comes from up here, where I have acceleration is v minus v naught divided by t minus t naught, or otherwise known as delta t, the change in time. And then I went through and solved and kept track of my units for dimensional analysis. And it came up with an acceleration of 7.66 meters per second. So let's go ahead and put that value here of 7.66 meters per second squared. All right, now let me get rid of some of this other stuff that's not needed. All right, so now I've got something new for you. Now I have a new problem where Bob accelerates from rest at 7.66 meters per second squared for 3.5 seconds. What is his final velocity? And as you look at this, you'll notice it's the exact same scenario as what we had before, but now I have a new set of equations. I have these three equations that you can see above, where we have the final velocity, represented by v, is equal to the initial velocity, represented by v naught, or v sub 0, plus the acceleration times the time that it was accelerating. How long was it accelerating for? It was that amount of time. So v equals v naught plus at. And I'm going to go ahead and start reading through the rest, just that way there's no confusion. We have v squared equals v naught squared plus 2a times x minus x naught. And please recognize that this here is the same thing as delta x. And so personally, when I write that, I usually just write it as 2a delta x, because it's the same thing. And then the last one here is x equals x naught plus v naught t plus 1/2 at squared, where this means the final position is equal to the initial position plus the initial velocity times the amount of time that the event occurred times 1/2 times the acceleration times, again, the same time that the event occurred. Just like what we had done before, I would like you to take the information from this word problem, write down the given, write down the unknown, find the appropriate equation to use, write down that equation without any numbers in the variables, manipulate the variables. So please manipulate, if necessary, manipulate the variables around before putting any numbers in, and then solve. In fact, really the only number you should almost ever put in is 0, because then it's going to cancel that variable out. But otherwise, try to manipulate the variables before putting in your numbers. Trust me, trust me, trust me, it is better in the long run. So with that, let's write down the things that are given and the unknown. So Bob accelerates from rest. So from rest, it is implied, it's not put in words, or excuse me, it's not put in numbers, but it is put in words, that the initial velocity is equal to 0 meters per second. You must be able to pick that out. Accelerates from rest at 7.66 meters per second squared. So the acceleration is equal to 7.66 meters per second squared. Does this for a time of 3.5 seconds. And what is the final velocity? All right, so that's what we're trying to find. So now that I've got those items, we're Look at how easy it is to find my equation. I need a v naught, an a, and a t. So if I go up here, excuse me, too far, I have a v naught, an a, and a t. Well, so be it. So I'm going to write that equation where v is equal to v naught plus at. I've written it without any numbers plugged in just yet. If you plug in numbers too soon, when anybody looks at your work, and specifically me, I'm not going to know necessarily which equation you used because the numbers might be different for each problem. The same thing goes with the AP test. So with that velocity is going to equal the 0 meters per second plus the acceleration of 7 meters per second squared, excuse me, 7.66 meters per second squared. I'll put parentheses around it so that way I can show the time is going to be 3.5 seconds. And plugging in those values, make that a little neater. There we go. And plugging in those values, this essentially goes away. The 7.66 times 3.5, that should give me a value of 26.8, and yes, that number should look familiar from before. 26.8, and what are my units? Well, let's see, I have, in fact, let me make sure that I express this a little bit differently. Let me say that I've got the 7.66 meters per second per 1 second. This is what I'm going to do. Let me extend the page. This is what I'm going to do to show you exactly where the units are going. 7.66 meters per second squared is the same thing as meters per second. Multiplying that by the 3.5 seconds, and that goes over 1. Notice that you have seconds here on the bottom and on the top, so those will cancel, leaving us behind just simply meters per second, which is why when you take the 7.66 times 3.5, that's going to give us the value of the 26.8. That's what we get from our calculator. And the units will be meters per second. That's what's left behind. So our final velocity is that 26.8 meters per second. And if you recall from the problem before, that is in fact the velocity that we determined. That was from the original problem way back when, because he went from 0 to 60 miles per hour, or 0 to 26.8 meters per second. So if I scroll back down, I've essentially just taken these 3 equations. It just all depends on the information that you're given. So let's say that this was the original problem, not the one that we have above, the one that we had done in a previous video. If this was the problem, this is the way that we would have to solve it. We would have to use this equation here in order to solve. And we just have to pull the information from the problem, write it down as given and unknown, and then determine which equation to use. All right, so hopefully that is helpful, and we'll see if maybe we can use any of these other equations in similar way. All right, so let's try something a little bit different. What if instead of asking you this question, what is his final velocity, instead, what if I asked something completely different? Now imagine that you don't know his final velocity. I never asked you that. Just imagine it if you may. Instead I ask, how far did he go? What is his change in position, essentially? How far did he go? Well, again, I haven't really asked you what his final velocity is. You don't know it. So you don't know this. You don't know this. You're probably catching on as to which equation it is that we're going to use, but we're going to take our traditional method in order to determine exactly that. So let's start from scratch. Let's determine what the given and unknown is. So what is given? Again, we have an acceleration that is 7.66 meters per second squared, or meters per second. We have a time that is equal to 3.5 seconds. We did say that he started from rest, so his initial V naught, his initial velocity, is 0 meters per second. We don't know the final velocity. In fact, I could write that in. Don't know the final velocity. And how far did he go? Let's just go ahead and say that it's delta x. It's the change. It's the x minus x naught. It's the change in position. This is what we really want to know here. So we have these other values, and as long as we have an equation that has the other values and not the one in the box, we're fine. So again, if we go back up, we have x and x naught. You recognize that if we were to subtract x naught from each side, we would simply have x minus x naught. So let me even rewrite that to say delta x is equal to all the other stuff on the right side of the equation. V naught, well, let's see, we have that, don't we? That is equal to 0. We have acceleration, yep, we've got that. We have time, yep, that's 3.5 seconds. We want to find the change in position. We have everything that we need. If I go back to the way it was written, so I have x is equal to x naught plus v naught t, x naught is 0, it's position 0. It might as well be. I can just say what is the final position, essentially, so long as the initial position is equal to 0 meters. It started off at the 0 meter mark. You can make that be anywhere you want it to be. So essentially delta x is the final position. Well, now that we have all the variables and we have in fact determined the correct equation, I'll put that at the top and I'll rewrite it. Always rewrite it. Always rewrite it. So x equals x naught. In fact, let me go ahead and rewrite it as delta x is equal to v naught t plus 1/2 at squared. Now that I've written that, I'm going to just kind of lightly cross that out because I know that I'm not going to need it since v naught is equal to 0. And I'm going to say that delta x is equal to 1/2 times the 7.66 meters per second squared times the 3.5 seconds squared. And notice that I'm putting the square outside of the parentheses. Sometimes the confusion that people will have is thinking that this square here under the second squared, sometimes people will think that that somehow means that the number is squared as well. It does not. It only applies to the units, not the number. When I have this outside of the parentheses, as I do, because inside the parentheses I have my variable, just like I have not changed the meaning there whatsoever. So since the number and the unit as well are in the parentheses, that square will apply to everything inside of the parentheses. So let's express that. Oh, I went too far. Too far. Okay, there we go. So I'm going to rewrite this out. In fact, let me pull this off to the left. That way I've got some room. And I'm going to rewrite it so that we've got the 1/2 times the 7.66 meters per second squared, okay, times, well, whatever 3.5 squared is. Let me go ahead and find that out. And that is 12.25, and I'm only doing this because I want to show you the dimensional analysis. It is 12.25 seconds squared. Because the number gets squared, this 2 here applies to the number and the unit. So we now can multiply everything out, and when we do that, we apply those numbers to the into the calculator. We will get a numerical value of 46.9, and the units you should know that x is it's a distance. It should be represented in meters. But let's make sure that we understand why. If I follow through with all of my units that I have above, right here I have meters per second squared. And from here I have multiplied by seconds over 1. since this cancels out, and let me express this. This is seconds times seconds, right? Right? Seconds squared is the same thing as a second times a second. And so it cancels out one of those, leaving behind just meters per second. That is dimensional analysis. Looking at the units as if they are variables and canceling them out appropriately. So that shows why it is. What am I saying? It's not meters per second. Let me move that back. We know it's meters. I was just saying that. What was my mistake? Right here, it is seconds squared over 1. My apologies. And again, this is seconds squared here. Those cancel out. You were probably thinking, he's crazy. I did it on purpose, just to make sure you're paying attention. We're left with meters, and our units are in fact meters because it is a position. It's a change in position. And so we have a final answer of 46.9 meters. Even I can make a mistake in my dimensional analysis, but as long as I'm paying attention, I'll catch that mistake in the end. So seconds squared, cancel out. We're left with meters. And we've shown how we can find, through this set of equations, we can find a different equation to use. All right, let me see if I can do one more. All right, let's do one last one. Notice I've changed the wording one more time. Bob accelerates from rest to 26.8 meters per second for 46.9 meters. So he's gone that distance. I'm giving you different information. Again, pretend I haven't asked you any other questions and this is the first time you've seen this format with Bob. What is his acceleration? So now I'm going to go through the same process. I'm going to write down the given and unknown. So the things that are given is that v naught, again, is 0 meters per second. So he goes from rest to a final velocity of 26.8 meters per second. The change in position is equal to 46.9 meters. So that means that x naught is 0 and his final x is 46.9. And then the acceleration is what we want to know. And there are other variables possible, like time. We don't know how long this was happening for now, but that may not be necessary. And so if we look through, I've got my variables here. And we want the top 4 to be in an equation. And looking through, let's see, we have v naught, we have acceleration, and we have essentially delta x in this equation right here. Look at it, and we have all of those things. Let's rewrite the equation. We're going to rewrite it. We have v squared equals v naught squared plus 2a, and let me go ahead and change that to delta x. X minus x naught is the same thing as delta x. I want to know the acceleration. So this is my perfect example where I can manipulate the variables and then plug in my numbers. I know you want to do it right now, but don't. Please get into the habit. You will see later as to why. Not later today, but you will see later. So I will solve for a. I'm going to say that v squared minus v naught squared equals 2a delta x, and then I'm going to divide each side by 2 delta x. So I'm going to say that the acceleration is equal to v squared minus v naught squared divided by 2 times delta x. Now I simply plug in my variables, make sure I keep track of my units, and solve. Plug and chug, if you will. And so v is 26.8, and that's going to be meters per second. I'm going to put that in parentheses, and my square goes outside of it. If you want, you can keep track of your dimensional analysis. I know that I'm going to have a final answer of meters per second squared because I have meters per second, because I have meters and meters per second. So I know that will be my final unit. Minus, let's see, 0 meters per second, and that's squared, but that's really not going to be of much use to me. Divided by 2 times the 46.9 meters. And I'm just taking a step back, like making sure that I put squares in it where I need to and didn't leave anything like that out. And I think it looks good, so let's go ahead and plug in our values. And if you did it right, you would get a value of 7.66, or at least that's where it's going to round off to. And that is, in fact, going to be meters per second squared. Let me just finish off by showing you why it's meters per second squared. Make sure we keep track of those units. This is the same thing. Let's see. Let me look at the units. Let me do the math with the units only. So ignoring the numbers, right? I don't care about the numbers right now. I already know what the final answer is in terms of numbers, but the units are going to be meters per second, that's squared, and that's going to apply to everything, divided by meters. So that is the same thing as meters squared divided by seconds squared, and all of that divided by meters. So you will notice that this here, if I rewrite it, that's the same thing as meters times meters. And one of those meters will, in fact, cancel out, again leaving me with meters per second squared. So that is my dimensional analysis showing me why I have meters per second, or meters per second squared. All right, so I think I'm going to finish up there. Here are the three equations. We need to learn how to show the given, show the unknown, show the proper equation, and pick out that equation and solve using dimensional analysis. That right there, if you can do everything that I've gone over here in the last 21 minutes or so, you are in good shape. So practice through this, come back, look at the video if you need to. You need to memorize those three equations. It's crucial. And remember that acceleration is meters per second, meters per second squared. All right. Have a good one, and good luck.